A PNP bipolar junction transistor is the counterpart to an NPN transistor, working in basically the same but opposite fashion. So the easiest way to understand how a PNP works is to compare it to the NPN. Structurally, where the NPN transistor consists of a section of P-type material sandwiched between two N-type sections, the PNP transistor has two P-type sections with a region of N-type material in the middle. In terms of usage, both transistors use the same amount of current at their base terminals to regulate the current flowing between the other two terminals. However, the direction of those currents is different between the two types of transistors. The control current for an NPN flows into the base terminal, and the larger regulated current flows from the collector to the emitter. In a PNP, on the other hand, current flows out of the base terminal, and the regulated current through the transistor flows in the opposite direction, from the emitter to the collector. One key difference between the two types of transistors is that in NPN transistor, electrons are treated as the important carriers. But in PNP transistors, the important carriers are the holes, which are the absence of electrons and represent positive charge. So, unlike the emitter in an NPN transistor, which emits electrons, the emitter in a PNP transistor emits holes. Those holes travel from the PNP's emitter to its collector terminal. And since by convention, we say that electric current flows in the direction of the holes instead of the direction of electrons, the conventional current through a PNP flows from its emitter to the collector, along with the holes. The schematic symbol for a PNP looks similar to the symbol for an NPN, except the arrow is pointing in the opposite direction, to indicate that the current through a PNP flows into the emitter. Since the current through a PNP flows from the emitter to the collector, the voltage at its emitter terminal will always need to be higher or more positive than the collector terminal. That's the opposite of an NPN transistor, whose collector voltage is always higher than the emitter. Since it's common practice to organize schematic drawings such that the circuit nodes near the top of the page are at a higher voltage than nodes near the bottom of the page, you'll usually see PNP transistors drawn with their emitter terminal at the top because it's at the higher potential, whereas NPN transistors will have their emitter terminal at the bottom because it's lower. In both cases, the arrow on the symbol is always connected to the emitter. Now, I have a hard time remembering which symbol is the PNP and which is NPN, so to keep things straight, I like to use the mnemonic not pointing in to remember that the arrow on an NPN transistor is pointing away from the bar. It's a slightly odd-sounding negated statement, but it works. I don't have a similar mnemonic to describe the PNP, so if the not pointing in statement doesn't apply, you're looking at a PNP. A PNP transistor has the same three operating modes as an NPN. In cutoff mode, it acts like an open circuit to block current between the emitter and collector. In the active mode, it lets some amount of current through, proportional to the base current. And in the saturation mode, it acts like a short circuit, allowing current to freely flow between the emitter and collector. The conditions that cause PNP transistors to behave in these three operating modes are basically the opposite of an NPN transistor. For that top diode-like junction between the base and emitter to become forward biased, the voltage at the transistor's base needs to drop below the emitter voltage by a certain threshold, which is usually around negative 0.7 volts. I've chosen to describe that value in terms of the base voltage minus the emitter voltage, so the value is negative, indicating that the base voltage is 0.7 volts lower than the emitter. For compactness, I'll use the standard label of VBE to indicate that difference between the base and emitter. If VBE is greater than the negative 0.7 volt threshold, the PNP transistor will be in the cutoff mode. The top diode-like junction is off, so the transistor blocks any current from passing through it and acts like an open circuit. When the base voltage drops low enough below the emitter to reach that threshold, the PN junction between the emitter and base acts like a forward bias diode and turns on, allowing the transistor to begin operating in the active mode. In the active mode, the amount of current passing through the transistor will vary based on the amount of current flowing out of the base. The transistor will allow a proportional amount of current to flow out through the collector based on the transistor's individual current gain or beta factor. The active mode PNP transistor will produce a collector current that is equal to beta times the base current. All of that current flowing out of the base and emitter terminals needs to come from somewhere, so in accordance with Kirchhoff's current law, the current flowing into the emitter terminal will be equal to the sum of the base and collector currents exiting the transistor. As the amount of base current increases or decreases, the emitter and collector currents will follow these equations to rise and fall too, as long as the transistor remains in the active mode. If the base current increases too much, the PNP will become saturated. The emitter terminal has maxed out the amount of current it can draw from whatever source it's connected to, so the saturated transistor no longer follows the linear relationship between the base and emitter currents. Just as with an NPN transistor, when a PNP becomes saturated, it acts like a short circuit for current between the emitter and collector. But there will still be a small voltage drop between those two terminals of around minus 0.2 volts or less. Again, I've made this value negative to indicate that the collector is at a lower potential than the emitter. Since there is a negative 0.7 volt drop from the base to the emitter, and only a minus 0.2 volt drop from the collector to the emitter, the voltage at the base terminal of a saturated PNP will be lower than the voltage at either of the other two terminals. The emitter voltage will be the highest, and the collector will be slightly below that. If I look at that alongside the voltage conditions required for an NPN transistor to be in the saturation mode, I can see that the greater than and less than symbols are just oriented in opposite directions. In fact, for each of the three transistor operating modes, the voltage relationship between the emitter, base, and collector terminals will have the opposite polarities for NPN versus PNP transistors. Just flip the greater than and less than signs around to convert the expression for one type of transistor to the other.